All right. Sorry about Tuesday. I got something in my eye. I tried eye wash. I literally sat there listening to an audiobook with my eyes shut for most of the day. And finally it fucking just stopped hurting. Previously we were working on derivatives of logs and natural logs. These were the two things that we had found, and we had left you off with find ddx of the natural log of x squared cosine x over the square root of 1 plus x. That was your challenge to go home and figure that out. Did anyone bother to do it? Good. At least some. So we could treat this as ddx of natural log of u, and that would be du natural log of u times du dx. If we set u equal to x squared cosine x over square root of 1 plus x. All right, so if I do that, this becomes the derivative of the natural log of u. du natural log of u, du dx. This part is just 1 over u. We need to figure out du dx and then replace u. So if we do du dx, this is actually going to be a pain in the butt with the quotient rule because we have a product on top. So rather than doing the quotient rule, you could have done the quotient rule. If you did the quotient rule, that's your high and that's your low. Instead, I'm going to write this as u equals x squared times cosine of x times 1 plus x to the negative 1/2. And show you the full firing power of the product rule. This is like A times B times C. We've only done 2 before, but when you do more than 2, du dx here we'll have A prime BC plus AB prime C plus ABC prime. So I just take the derivative in order, do one term at a time. The derivative of A is 2x. So I have 2x times BC is cosine x. I'm going to put this back over the square root of 1 plus x, since I didn't take the derivative here. And then I've got plus b prime, which means x squared stays the same. What's the derivative of cosine?
Negative sine x.
Negative sine x, thank you. And c didn't change here, so I'm going to do c, leave that as its original form. And then I've got x squared cosine x, that's my AB. C prime is going to be, I bring the exponent down, lower the exponent by 1, and multiply by the derivative of the inside. The derivative of the inside is 1. So if I would put this together, plus, well, minus, I have an x squared cosine x on top, and I have 2 over this to the 3/2. That to the 3/2 is 1 plus x times square root of 1 plus x. 1 plus x to the negative 3 halves is 1 over x, 1 plus x, square root of 1 plus x. All right, so if I want a common denominator, I need to multiply the first one by this. So I have 2 times 1 plus x times 2x cosine x minus x squared sine x, all minus x squared cosine x over 2 1 plus x square root of 1 plus x. That's just the du dx. So 1 over u is just going to be u flipped over. I will have square root of 1 plus 1 plus x over x squared cosine x. That's my 1 over u. And I still have this marvelous thing that I did not bother to multiply out. Now I can see the square root of 1 plus x on top and bottom go away. There might be more shit that cleans up if you multiply out the stuff on top and factor it out. But we got the derivative done. For those of you that did not read the announcement, the midterm, or the not midterm, the first exam scores are up. Overall, the class didn't do that great, but it was not different than most calculus classes. Most calculus 1 classes are a train wreck for the first exam. In an effort to encourage you guys to keep going and double down, maybe do more homework and stuff, you can take the exact exam you took is up in the announcements. You can take it at home. You just submit it online by Tuesday or bring it in. You can seek help at the math lab or from tutors or whatever. It says exam on it, but if you show the people in the math lab the announcement where it says Professor Jones says you can go get help, I will average out your 2 scores. You don't have to do it. If you already got a good grade and you're happy with it, you don't need to do it. But if you do, I'll average it out. But the questions on the makeup are no partial credit. You either get it right or you don't. Which means show your work, have the right answer. Make sure you got limit listed the whole way until you don't need it no more. And if you after class, if you come up and get your test, if you didn't get it before class, you can see what you got wrong. All right. Ready for another question? We're still doing, oh wait, I see people still writing. Everyone ready? Okay. Never know when a pin's moving, if they're doodling or just adding extra script, or if they're still taking notes. All right, new idea. We have y equals x squared times the cube root of 7x minus 14 all over 1 plus x squared to the 4th power. And we could do this derivative normally. We're going to find y prime. But we're going to do it a different manner. We've learned how to do it with the quotient rule. We've learned we could move this to the top and make that a -4 and do a product rule. We're going to do something called logarithmic differentiation. This is the good shit right here. I think we can all agree this looks like it'd be a clusterfuck to do with quotient rule or some shit like that. What we're going to do is treat each side as the argument of a natural log. This is the heart of logarithmic differentiation. So I'm going to have natural log of y equals natural log of x squared. I'm going to write this cube root as 7x minus 14 to the 1/3. 1 plus x squared to the 4th. And now the key is you don't take the derivative right away. Otherwise, that doesn't help you at all. Use the properties of natural logs to break this up. When we have two things on the inside multiplied, they become added if we separate them. And if it's divided, it's subtracted. Another property we had with logarithms is if there's an exponent on the argument, you can bring it down as a coefficient. At this point, you take the derivative with respect to x of both sides. The derivative of the natural log of y is 1 over y times dy dx. So it's got implicit differentiation in it. The right side, the derivative of the natural log of something is just 1 over that value. So this becomes 2. I'm going to be explicit about it. I'll clean it up a little bit second, but I'm writing it as 2 times 1 over x plus 1/3 times 1 over 7x minus 14. Then we have to take the derivative of the inside, which is 7. Then minus 4 times the derivative of natural log is 1 over that value. Then times the derivative of the inside is 2x. La 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 la. So let's clean it up. It looks like I could factor a 7 out of this thing right here and make that 7 times x minus 2. And that would cancel with one of the 7s up here. That would cancel that 7. So I have 1 over y dy dx equals 2 over x plus 1 over 3 times x minus 2 minus, I've got 4 times 2x is 8x on top. And the bottom is 1 plus x squared. I multiply through by y, and I get dy dx equals 2 over x plus 1 over 3 times x minus 2 minus 8 over x times 1 plus x squared. Everything we had before times y. But I'm going to get rid of that y. So move the y over. Multiply by y. Y in terms of x, though, was, cross that out, what we had up here. X squared cube root of 7x minus 14 all over 1 plus x squared to the 4th. Now, there was more steps at the beginning. We had to convert it to a natural log. We had to manipulate it using the properties of logs. But the derivative, look how much easier the derivatives were. The derivative was a whole lot easier. So that's the idea about sometimes using natural logs to clean things up. What's really helpful about this process is when it's in a natural log, when we have logs, we can bring the exponent down. So logarithmic differentiation allows us to bring exponents down as coefficients. When might that be helpful? I'm going to go with super helpful. Yeah,
And when you got fractions at the next one.
when we have fractions as an exponent, will help definitely there. It makes dealing with the chain rule portion a lot easier. There's one more like big one I had in mind, but fractions definitely so. Even negative exponents is along with fractions. Everything we've had so far, the variable has not been in an exponent. Sometimes our variables have the exponent, or our exponents have the variables. And we don't have any way of doing that. The exponent is a variable. And we will see this today. In fact, I mean, yep, I do. I even have it on the next one. As a reminder, I'll be at the Mesa Center over on the Visalia campus this Saturday from 9 to 12. You are free to come in and ask questions. I've had calculus students come in, a couple students that have dropped the class, but they were here the first couple weeks. They dropped it before the exam. But I've had other calc students from other classes come in and they're just using the whiteboards, going over problems, and I'm guiding them and stuff. It'd be good practice if you have Saturday morning free and want to juice up on your juice up. What a fucking weird phrase. Juice up. Expand your calculus abilities, maybe freshen up on algebra and trig. All right. Next question. So we want to find the equation of the line tangent to the curve y equals x to the x at the point x equals e. So it ends up being its own exponent. So like when x is 1, it's 1 to the 1. When x is 1/2, it's 1/2 to the 1/2, or square root of 1/2. When x is 2, it's 2 squared. When x is 3, it's 3 cubed. It's kind of neat. This is a very rapidly growing function. Like even faster than those, like one of the fastest growing functions there is. X to the 10th is 10, or x equals 10 is 10 to the 10th power. What is that? Fucking 10 billion? X equals 10 and we're already up to 10 billion? That's huge. Y equals x to the x. So, treat each side as the argument of a natural log. I'm going to do that. And so I have natural log of y equals, and I'm going to bring that exponent down, x natural log of x. And this just got a whole lot more manageable. I wouldn't even know how to tackle x to the x. But the natural log of y, the derivative of that with respect to x is 1 over y dy dx. So now we're doing d dx of both sides. The right side is a product rule. X times natural log of x. So I'll take the derivative of the first and leave the second one alone. And then I'll leave the first one alone and take the derivative of the second. So dy dx equals y times natural log of x plus 1. I'm going to write it as 1 plus natural log of x, because sometimes that 1 gets confused for the something inside the natural log. And that means this is x to the x times 1 plus natural log of x. Because that was what y was. Still need to find the tangent line. We can do y minus y1 equals m times x minus x1. So our x1 is e. They gave that to us at the point x equals e. Y1 at that point is x to the x or e to the e. Which is just a number. It looks trippy, but like, where's my e? E raised to the e. Rude. Why is that a problem? E to the first power is 2.71. And then I'm going to do e raised the answer to that. It doesn't like that. Maybe my calculator's a little bitch. E to the e is just a number. Maybe it doesn't know how to calculate e to the e. Does my cell phone? Just trying to get an approximation. It's got to be a little bit less than, I don't know. It's got to be under 27 because 3 to the 3 power is 27. What is e to the e? Ooh, there we go. E exponent e. That's approximately 15.15. Oh. Just a number. So, and what's our slope here? Our slope is this. At x1, e. So m is e to the e times 1 plus natural log of e. What is the natural log of E? This shows you how rusty you guys are on some of this shit. This is one of the most well-known, easiest ones to do. Natural log of E is 1. So 1 plus 1 is 2, m equals 2e to the e. So this is gonna look like a ridiculously looking funny question or equation. But we got y minus y1 is y minus e to the e equals 2e to the e times x minus e. And we could clean this up, but really, it's okay. Any questions? That's some next level shit right there. X to the x, right? It sounds kind of neat. So if you don't know how to tackle a problem, because like, let's face it, if you see y equals x to the x, and you just try to write down an answer, you fucking cheated. This is not do it in your head work. This is like, most people are like, I don't even know what the fuck to do. So try using natural logs to, the trick is, the helpful thing is, if the exponent has a variable, use logarithmic differentiation. Let's take a 5-minute break because we're going to start 3.3 in a second. So if anyone needs to go to the bathroom or anything, here's your chance. All right, 3.3 is on. What is this shit on? Derivatives of exponentials and inverses. Inverse trig functions. So here's the basic idea. We have y and it equals some inverse function. Exponentials are inverse functions. They're inverse functions of logarithms. So these are all in the category of inverse functions. The approach is rewrite as f of y equals x. F and f inverse, or f and f to the negative 1 are inverses. So or you can, or swap x's and y's. That does inverses as well. So we got f of y equals x. And if I take the derivative with respect to x of both sides, I have f prime of y times dy dx. That implicit differentiation just keeps coming back. The derivative of the right side is 1. That's another mistake I saw. Derivative of a constant number, like derivative of 3, is 0. People weren't like getting rid of the derivative of a constant. They were leaving it there. So dy dx is 1 over f prime of y. But y was f inverse of x. That's like the general thing of what's going on. And to know if there's going to be an inverse, recall an inverse exists if it passes the horizontal line test. Or B, the function is either increasing on its whole domain or decreasing. On the whole domain. Exponential functions fall in that category of B. They also pass the horizontal line test, but this isn't the most exciting thing. It's a little bit easier to see putting this into effect. All right. Does anyone need it longer? Let's take a look at this idea that it's increasing or on its whole domain. Let's give an example because you're like, what's going on here? What we want to do is find the derivative of the inverse of f of x equals 2x cubed plus 5x plus 3. Now, I don't want to graph this because graphing this sounds like a tedious pain in the ass, right? But I can see, because graphing is how you check the horizontal line test. I can check to see if it's always increasing or always decreasing by checking the derivative. The derivative is the slope. If the slope is always positive or the slope is always negative, it's always decreasing or increasing. So f prime of x, let's just say 2x cubed, sorry. The derivative of 2x cubed is 6x squared. The derivative of 5x is 5. And the derivative of 3 is 0. So for all x, f prime of x is greater than 0. This is an increasing function. So it's going to pass the horizontal line test. That's a handy way of checking to see if it passes the horizontal line test. And when you first learn about the horizontal line test, you don't know derivatives because it's an algebra. So how do we find the derivative? We're going to say y equals 2x cubed plus 5x plus 3. And we're going to swap x's and y's. Put my x over here, and these are my y's. Now we'll do the derivative with respect to x of both sides. Remember, y has implicit differentiation. So the left side is 1. The 2y cubed, we bring the 3 down, multiply it, becomes 6y squared times the derivative of y with respect to x. And then we have plus 5 times the derivative of y with respect to x. And the derivative of 3 is 0. So I'll factor out the dy dx. And we'll divide by the 6y squared plus 5. So dy dx is 1 over 6y squared plus 5. So this was the inverse. We took the derivative of it. So this is like d dx of f inverse of x. Because our y here was the inverse. When we did the old swap-a-root, y became f inverse. And we should probably put y back in. That's squared. So this gives us a method of finding the derivative of the inverse. And the other takeaway from this little section right here is if functions that pass the horizontal line test are either increasing or decreasing functions. That's what this is called right here. An increasing function or decreasing function. And for it to pass the horizontal line test and have an inverse means the increasing functions or decreasing functions are 1 to 1. That's what inverse means, being able to do a y equals x swap. It passes both the horizontal line test and the vertical line test. And 1 to 1 functions have an inverse. That's the takeaway from that. So we can use the slope to find out if something has inverse, and how to find the derivatives of the inverse. So we did derivatives of natural logs and logarithms. Maybe we should do their inverses as well. Let's find if f of x equals b to the x. Find f prime of x. So I'm going to say y equals b to the x. And rather than doing the swap, we already had an easy method of dealing with something that had x in the exponents. Let's take the natural log of both sides. I'm going to get the natural log of y equals the natural log of b to the x, which equals x natural log of b. And when I take the derivative of both sides, I get 1 over y times dy dx equals the derivative of x natural log of b. X is the variable. The ln of b is just a constant. So this just gives us ln of b. We multiply through by y, and we get y times the natural log of b, but y was b to the x. So the derivative of b to the x is b to the x natural log of b.
I have a question.
Yeah,
Why did the x go away?
we took the derivative of it with respect to x.
Um,
Sorry, I didn't write that down. I said it, but I didn't write it. Thanks for pointing that out.
Jones,
Yeah,
how come you didn't use the product for x times natural log?
we could.
Would it be the same thing?
Yes, because natural log of b is a constant, so when we take the derivative of it, it's 0. So that term is gonna go away. But we'll do it real quick. So like we can do product rule on this. This is a good question. Like why is the derivative of x times a constant just the constant? I could do d dx of x times the natural log of b plus x times d dx of the natural log of b. That's the product rule. The derivative of x with respect to x is 1. So 1 times the natural log of b plus natural log of b. B is a number, so natural log of b is a number also. The derivative of a constant is 0. This is just a constant. And so that goes away, and all we're left with is natural log of b.
Let's say it was natural log of x, that'd be a variable, so it'd be 1 over x.
Yes.
Oh, but since it's a constant, it's just 0.
Yes. This is like the equivalent of doing the derivative of 2x equals 2. It just doesn't look like a constant because it says natural log of b. I totally get the question. Anybody else have another question? Like, let's make it a constant that you recognize. Let's say b equals e. Our problem becomes f of x equals e to the x. So find d dx of e to the x. Or f prime of x. We can follow the steps up above, or we can take advantage of this property, b equals e, and say that d dx of e to the x equals e to the x natural log of e. We're just following this pattern, right? This formula right here. But natural log of e is 1. So d dx of e to the x is e to the x. Boom. I don't know about you, but I think that's fucking awesome. E to the x is its own derivative. The function evaluated at any point gives you the slope of the tangent line of the function at that point. The e to the x is like a magic fucking function. It's the most magical of functions. This led to one of my most favorite Super Mario Brothers movie memes with fucking Bowser, like the little ice wizard dude going, "Do you yield?" And Bowser's like, "I do not." And it had, I don't know, do I have it here? Yeah, I do. So Ice Wizard Guide's DDX and Bowser is EDX. He's like, nope, you're no fucking threat to me. This came out like right before the movie even was really fucking airing. It was based off a previous. I fucking loved it. That's really cool. It's the only thing that does it. B to the X is close, but it has an extra constant there. E to the x is its own derivative. So you can take the derivative at 15 fucking times and you still get e to the x. That's fucking deep. All right. Let's kick it up a notch. Let's do d dx. X squared plus 1 cosine x. I'm going to do this. I'm going to say y equals x squared plus 1 to the cosine x. So now I'm looking for dy dx. That's what I want. So I'm going to take the natural log of both sides. And then I will bring that exponent down out in front. And let me pause and let you guys finish from here. Yeah, that's what it is right there. All right. The product rule, right, on the right side? We're gonna take the derivative of the first, which is negative sine x. We leave the second one alone. And then we leave the first one alone. And take the derivative of the second, which is a chain rule. We do the natural log first, 1 over the argument. And then I take the derivative of the inside, which is 2x. So if I were to clean that up a little bit, I would say, I'm gonna put the positive one first, the 2x cosine x first, over x squared plus 1, minus sine x, natural log of x, or x squared plus 1. And then we clear the y by multiplying both sides by y. And we get dy dx, which is what we're looking for. Which is y, which is, the y is the x squared plus 1 to the cosine x. And we have times what we have in parentheses right there. I'm going to take this a little bit further, just because something happens here that you may not recognize. And it's worth seeing. I'm going to get a common denominator by multiplying this by x squared plus 1 over x squared plus 1. And if I do, And before I do the next thing, I'm gonna just remind you, if I had x to the fourth over x, this equals x to the 4 minus 1. Well, now I don't have a 4, I have a cosine x. This part is to the first power. I can combine it with this like this. And then we still have our fun little but that's the derivative of that function. So the only reason I took it a little further is I wanted to point out that even though it's a weird exponent, cosine x, we still had the same thing on bottom. The bases were the same. Bases were the same. So we could combine to make that. And that's not something that's intuitive, because you're used to only doing it with numerical exponents. All right, you guys ready to see the inverse trig functions? Where's the, oh yeah, where's the fucking enthusiasm? This is good shit. It's early, right? It's not that early though, it's 9:30. Where's the enthusiasm? Where's the joy? Who's having fun? Are you having fun, Edgar? All right. Everybody looks like they're done writing, so we'll go on. Let's find the derivative of sine inverse x. So just like I did in the last one, I'm going to let that inside equal y. And if I do that, this means sine of y equals x. That's another way of writing the or undoing they're equivalent. So now I'm going to take the derivative with respect to x of each side. So the derivative of sine is cosine. But this was a y, not an x, which means we need to take the derivative of y also. Chain rule this bad boy. We get dy dx. The right side equals 1. So dy dx is 1 over cosine y. And cosine or y is sine inverse x. So that's d dx of sine inverse x. But that cleans up. I'm not gonna leave it like that. So to go from here, I'm gonna say theta equals sine inverse x, which means sine of theta equals x, or x over 1. Sine is opposite over hypotenuse. Opposite is x, hypotenuse is there. Using the Pythagorean formula, this is 1 minus x squared, square root of 1 minus x squared. I got that doing, like if we called this a, I got a squared plus x squared equals 1 squared. That's the Pythagorean formula. So a squared equals 1 minus x squared. So a equals plus or minus the square root of 1 minus x squared. But a is a length. So we're gonna make it positive here. So that's where I got the 1 minus x squared. So if I want cosine theta here, because I said theta equals sine inverse x, I'm doing cosine theta. D dx of sine inverse of x. Cosine of theta is adjacent over hypotenuse, which is square root of 1 minus x squared over 1 from our picture. So cosine theta, which goes on the bottom, is square root of 1 minus x squared. That is the derivative of sine inverse of x. Oh, I know another thing people had problems with, but it wasn't algebra related. It was definitely calculated. People didn't know the derivative of tangent on test or secant. They were mixing that stuff up. So I strongly recommend making flashcards for any of these things that, like, there's 6 different trig functions, which means there's 6 different derivatives. It's worth making flashcards and until you have them memorized. Just as there's 6 trig functions, there's going to be 6 inverse trig functions. So we're going to have six of these things a little bit. We just showed sines. We're going to show tangent next. And then I'll give you the other 4. You guys ready for your tangent? No, I see some pins still gone. Give me a second. La, 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 la. Take a look at tangent. Well, tangent inverse. We're gonna follow that same pattern. I'm gonna say y equals tangent inverse of x, which means x equals tangent of y. Take the derivative of both sides. I get 1 on the left. What's the derivative of tangent? Secant squared. So this is secant squared and it's y. So we got a dy dx. So dy dx equals 1 over secant squared y. Which equals 1 over, I'm going to replace the y with the tangent inverse. And I think this is a little harder to do. So I'm going to rewrite this the way it is. So a lot of students forgot this. When you had to take the derivative of secant squared x is really secant x, that thing squared. This is 1 over secant tangent inverse x squared. Students were missing that earlier. On the test, I saw this. ddx of secant squared x is not secant x tangent x. That's just part of it. You really want to rewrite this as ddx of secant x squared and do the chain rule. That's easy. That one was easy to miss. So that was a mistake I saw in the exam. It's doing that. So we're here. So just like we did in our last thing, we're going to draw a picture. I've got tangent inverse x equals some degree theta. So x equals tangent theta. Theta or tangent is SOHCAHTOA, opposite over adjacent. So opposite is x, adjacent is 1. This is the square root of 1 plus x squared. And you could do square root of x squared plus 1, but you're going to find that it might be easier to memorize it in this order. So secant of theta, cosine theta is adjacent over hypotenuse. So secant theta is hypotenuse over adjacent, which is the 1 over cosine theta. So hypotenuse here is 1 plus x squared, square root, and adjacent is 1. So secant theta is square root of 1 plus x squared. And I end up with ddx of tangent inverse of x. When I plug that in, I've got a square root and a square. This is just 1 over 1 plus x squared. Yeah,
How do you get square root of 1 plus x squared?
so the hypotenuse, this is a right triangle. This is the hypotenuse for this angle. Oh, this is always the hypotenuse. For this angle here, this is the opposite, and this is the adjacent. So I got, how did I get this right here?
Use the.
I use the Pythagorean formula for that one. Now I'm just filling in what these are. Like I did SOHCAHTOA. So cosine is adjacent over hypotenuse, which means secant is that flipped over. Because that's the relationship between secant and cosine. Secant theta is 1 over cosine theta. I could have done cosine theta here. Cosine theta is adjacent over hypotenuse. And then I flip this over, flip for secant. Does that make sense? If it doesn't, it's trig skills are rusty. You want to brush up on those. That's all that is. There was no calculus in this shit right here. That was all trig. That shit just keeps coming back. It's like bad STD. You see it now? Okay. All right, let's give you a list of the 6 inverse trig functions. So ddx of sine inverse x. This is our good old 1 over square root of 1 minus x squared. We already calculated that one. If we do ddx of cosine inverse of x, you're going to find it's almost identical to sine inverse of x. We have 1 over square root of 1 minus x squared, but this is negative. Kind of like derivatives of sines and cosines, one of them introduces a negative. If you took the derivative of cosine, it introduces a negative. The derivative of cosine inverse introduces a negative as well. But other than that, it looks identical to sine x. In fact, that looks identical to negative sine inverse of x, or negative derivative of sine inverse of x. I don't know if that helps you remember them. Then we have the other one we just did, our tangent one. Equals 1 over 1 plus x squared.
Yeah.
So our ones that are related to it, cosecant is related to sine, it's the inverse of it. Let's do cosecants next. ddx of cosecant inverse. This is -1 over x times the square root of x squared minus 1. It should say cosecant right there. The derivative of secant inverse x. Just like sine inverse and cosine inverse are different by a minus sign, so are cosecant and secant. And finally, we have cotangent. -1 over 1 plus x squared. An easier way to remember this, the derivative of the inverse trigs that start with a C are negatives of their counterpart. Partners. Derivative of cosine inverse is the negative sine inverse. The derivative of cosecant inverse is the negative of secant inverse. And the derivative of cotangent inverse is the negative of tangent inverse. But strongly recommend flashcarding it. I don't know if you guys are aware. I'm going to put a flyer up for it. I'm going to load it as an announcement. Let me put it on screen real quick. Next Wednesday on October 4th over in Visalia in the John Muir building from 4 to 7, they're doing a study techniques and test prep workshop. It's 3 hours. There's raffles. There's dinners. They're going to give you pizza. They'll show you how to study for some STEM classes at a college level. Give you some pro tips from people that have gone through this, have graduate degrees, or are working on their graduate degrees, and how they have thrived in college. So, if you're free next Wednesday, right in the evening, 4 to 7, I'd go over to Visalia and just check it out. Raffles and prizes and stuff like that. I'll put an announcement up this to remind you about it. But it might help you for the next test. All right, so we got a couple more examples we want to do here. Let's find y prime if y equals sine inverse of 1 minus t. So y prime here means dy dt, not dy dx. So I recommend, since we've got something weird going on the inside, I'm gonna say, do a U substitution, let U equal that inside. So now y prime is gonna equal dy du, du dt. And du dt is -1. So I got y equals sine inverse of u. So when I do dy dt of that, I have the sine inverse, that's the 1 over the square root of 1 minus, in this case, u squared. And then I have du dt, which is -1. And we didn't start with y, so we're not going to end with y. Or we didn't start with u, so we're not going to end with u. I am going to put 1 minus t back in. 1 minus t squared. And the -1, I'll just move on to the top. And that's how I'm going to leave it. I don't know when I did the chain rule if I pointed out to you how I remember it. So I'm going to expand on it right here. I had dy dt equals dy du dt times du dt. That's the chain rule. With t's here rather than x's. If I treated these like fractions and multiplied them, what would I get on the right side? Wait, what? Just look, don't treat this in relationship to the problem. Just look at like this right here.
Get the same thing.
You get the same thing, like if we treated it as a fraction, the du's would cancel and we would get dy dt. That's not really what's happening, but it makes it an easy way to remember. Like if you want to write it with the u substitution in there, this is what needs to happen. When you expand it out, you should be able to collapse them back again and get what you started with. So that's how I remember what goes over what and what goes where. Like I know, like I gotta have a u, so I'm gonna, one of them's gonna have a u on top, one of them's gonna have a u on bottom. And it doesn't make sense to do the du on with the y. All right, one more quick example. Are we having fun? This is exciting. You think this is exciting? Guess what's coming up next week? Hyperbolic trig functions. Fuck yeah. You're gonna be like, why? So we got ddx of tangent inverse of the square root of x squared minus 1. So I'm going to say that's y. Y equals tangent inverse of square root of x squared minus 1, and we're doing d dx of this. This makes it a little easier for me to see. I can do dy dx equals dy du times du dx if I treat u as the inside. Square root of x squared minus 1. So du dx, this is u equals x squared minus 1 to the 1/2. So du dx is, I'll bring that power down, lower the power by 1, and then multiply by the derivative of the inside. And if I write this a little bit cleaner, this is x over the square root of x squared minus 1. That's du dx. And this becomes ddx of tangent inverse of u. We saw that was 1 over 1 plus the inside squared. And so, and then we have times du dx. So I'm gonna start plugging stuff in. I've got u squared, so if I square u here, u squared is just x squared minus 1. So I've got 1 over 1 plus x squared minus 1 times x over, I miss the 2's canceled, yeah, so square root of x squared minus 1. This actually cleans up a little bit more. Because if I work with that, that's just 1 over x squared. Finally, we can merge those. Which is crazy because that happens to be ddx of secant inverse of x. And that's it. Have a good weekend. I hope I hear from you or see you at the Mesa Center on Saturday if you need some help. Don't forget you can do that makeup exam. Try to write out all your work, get help when you need it. Try to get 100%. The idea is to not get someone to show you all the answers because that's not going to fucking help you on the next test. This is a mercy move on my part for you guys to get some extra help, like force you to go get some help and lock in some of your learning, that like the limits and derivatives of the first 2 chapters, because you need them on this later stuff. They keep coming back. Product rule, chain rule keeps coming back. I will see you guys on Tuesday.